Hello everyone, welcome back to the second lecture on um, cloud processing with Metashape Agisoft. So we just completed a little exercise looking at a very simple one-level flight for an area in Argentina that is a natural environment where we also did a DEM generation. And I would like to build upon this and would like to um, add a few more flights and do a more detailed analysis of the points and specifically include reference points. Because if you want to generate a high resolution digital elevation model and you would like to minimize the impact of camera distortion, it's very advisable to include ground reference points, and that's what we are going to deal with. So I'm going to build upon this by using the same workspace, and I'm adding a chunk, a second chunk, which is essentially just a second data source that we are going to work with. And as before, I'm going to add a folder with photos, and I'm going to add the same photos that we had before. So these are the one large-scale overview flight, the one that we also have processed. So this is here now in the location of the site here. This is a one-level flight, and I'm starting out by doing the camera calibration and making sure that I have different camera groups for the various flights. So I'm taking the first flight and putting them in a camera group. Again, it's very straightforward to do this by time because usually you have a few minutes between the flights when you change batteries. So now I have the 3 flights separated, but now I'm adding more photos that I have taken from that same mission. So I now add 357 photos, and you can see that there is this path that we have added in a separate flight. And as before, I'm going to create new camera groups for this. So this ended up in this first camera group, and I'm going to separate this out by looking at the end of the flight. You see there is, the end is 16:33, and the next flight is a couple of minutes later, 16:41. You know, changing battery, resetting sometimes the software. This is all part of the standard operating procedure for drone flights. And now I'm looking for that next times jump, which occurs right here. So we have been flying for several hours over several days. These are in 2 different groups now. We have almost 1,000 images. I am now adding the next folder. This is our folder with almost 1,000 images. So these were additional flights that were done, 99 cameras that were done at much lower elevation. You see these parts appearing here, the additional flights. And again, I'm going to the camera calibration. I have 1,058 images in here, and I would like to make sure that these are in different camera groups because that makes the optimization process much more feasible. And I'm looking for that time jump when this occurred, and I'm seeing that there is one time jump here, and I'm going to put this in a separate group, and then from 16:27 to roughly 16:44 we have had another group that then gives us almost 2,000 images, and now we are adding the last folder, a few remaining flights. I have a few remaining photos, 74 photos added from a last flight. and I'm doing the camera calibration to make sure that these end up in a separate folder as well. So we see that this one here, let's see where we have this jump here. We have this jump right here, that this ends up in a different folder. So let's look at these individual flights. So this is one flight that all pop up in one color. This is a second flight and a large overview flight. This is another camera group. This is another camera group. So these are these three flights here were the large scale overview flights. At the highest elevation, and then we put in a few additional flights at a medium elevation, and then flights more detailed at lower elevation, as you can see here. Again, the separation in the camera groups is not necessary, but it will help during the process of optimization, so I strongly suggest to do this. It's also the easiest to do the camera group separation when you load in the photos, because sometimes the names are the same, then it's very difficult to separate out by names, and sometimes the timing is off a little bit, so it's generally advisable to sequentially separate those into different camera groups. It makes it just easier to work with. Okay, so I just wanted to show you that we can also look at the model from the side. So if we, I'm sorry, that we can look at it from the side as soon as we have added the 3D information to it. So we can look at our cameras and see that the flights have been taken at different heights, right? So here you can appreciate the large scale overview flight, then we have done a flight at a medium elevation, and then we have done very detailed flight to capture a greater detail. So what we are going to do next is we are going to see if we can detect some of the references, markers that we have put out, and I'm going to see in my image library if I can show you an example of such a marker. And I need to scroll down a little, or I could also do it this way. I look at the model. I know that we have been taking quite a few markers here. So let's do this filter photos by camera. And now we can see, and here I can show you an example of a marker. So we have been putting out those markers in the field. Each of those targets have different names, and they can be automatically detected if the resolution is good enough. In order to pick up the markers, it's very advisable to do drone flights at a lower elevation, maybe 10 to 50 meters, to make sure that you get the high resolution ability to detect those center points. So you want to detect this center point here. Now let's see if we can do this automatically with Metashape. So these are the ready-made markers that come from Metashape, and these are markers that you can also generate and print. So if you go to print markers, you can generate those markers and print them out on a PDF page. We have printed them out on an A0 large kind of a fabric material so that we can put them out in the field. You don't need to use the markers that Metashape produces. You can also build yourself a cross or use some other symbol. The advantage of these markers that Metashape produces is that you can automatically detect them in the photos if the resolution is high enough. So let's do this. Detect markers. These are the 12-bit markers. And we can ignore the other options because we printed black on white. You can do it the other way around as well. So this detection will take a few seconds because we have to go to 2000 photos and each image is individually analyzed. So I will be right back once this processing is done. So when this marker detection is done, you will see that some markers have been detected. Here the markers 1 to 5 have been detected. I can show you an example of a detected marker. So this is a marker detected, and this has been detected because it has a fairly high resolution and can be automatically detected. Some of the other markers that are definitely there have not been automatically detected because the image quality may not have been high enough, or there were other problems with those images. So there is definitely, so for example, here in this image, this marker has been detected. This marker has not been detected because there is an overland wire partly going through it, so the automatic detection mechanism didn't work. And here is another marker that was not detected. That is just the case, or that's a common case, when you use those low resolution or lower resolution images. It certainly would have helped taking additional lower elevation photos to automatically detect these markers. But we can do this at a later stage. What I would like to do next is add the reference information. So these were targets. These markers have been measured in with a differential GPS. We had a base station. We had actually several base stations that allowed us to tie down the position down to the centimeter or sub-centimeter accuracy, and we are going to use those coordinates and assign it to the markers. This can be partly automatized. I first can show you the output of the differential GPS processing. So when we look here at our Excel spreadsheet, this is an output. I'm going to zoom in a little. This is an output from a standard open source GNSS processing effort. So we have the names, we have targets from 1 to 9 total targets. Here we have the UTM coordinates, and here we have the heights. I have two height columns because one is with the geoid and one is without the geoid. I also have the two columns showing us the XY uncertainty. Oops, making sure that I'm not moving this. The XY uncertainty here for this first target is roughly 10 centimeters, and the Z, the height uncertainty, is roughly 70 centimeters. So this was a little less constrained, but here, for example, for target 5 that we have measured for quite some time, we have a uncertainty of 1 millimeter and in the XY direction, and 2 millimeters in the V in the height direction. So these units are all meters, and these are UTM coordinates, zone 19 south. So you see that overall the error is pretty low. The error pretty much directly correlates with the duration of the measurements. If you measure your reference point for a couple of minutes only, you may have centimeter or a couple of centimeter accuracy. If you're measuring for more than 10-15 minutes, you get into the lower centimeter, sub-centimeter level of accuracy. So these are the input data that we have, and we can now bring those data into Metashape. So we can go to the reference tab and import the references, and the references that we have are stored in a CSV chart, for example. So I'm going to So let's bring in those markers, and we can go to import reference. We open up that CSV file that we just looked at. We make sure that the coordinate system is set properly, and then we have different columns that we have to assign to the proper number. So label column 1 is 1. We don't have an enable flag. We can click this off. Our timing, we don't need to worry about. Our 1, 2, 3, 4, fourth column is easting. And our fifth column is northing. So we have the label, we have easting, we have northing, we have altitude. We just take our geoid altitude, and then we have the accuracies. The accuracies are in a way that we have this is the horizontal accuracy, so this is easting accuracy, and this would also be a northing accuracy. So we are not distinguishing between easting and northing, but we have a separate altitude accuracy. And then we don't have information about the rotation, yaw, pitch, roll of the camera. We don't have these additional information. And we want to make sure that we are importing everything starting in the second row, because the first row still contains some comment information. So bringing in these in, I'm seeing that the naming, for example, has not been properly matched. So we have a target 1, but we call our target 0.1 in this file. So we need to make sure that this naming is correct. So we stop this. This is a typical problem that occurs, and we are going to edit that file. So we are going to edit our file that we just had, our CSV file, and we make sure that our first target is called target 1. So need to make sure that this is then target 8. This is target 5. Need to make sure that you don't have the auto correction on. This is target 9 that exists here. This is target 4. This is target 3. This is target 2. This is target 7. Oops, making sure that this is correct. Target 7, and this is target 6. So let's make sure that I'm doing the auto correction removal here. This is very important to have the same name of the target column or of the label column as it is used in Metashape. Otherwise, we will not find a match. So if we bring this up again and we reload our positions, now we have a naming scheme linked to the markers identified by Metashape. All the other settings remain saved, but now we can find a match for target 8, right? Because our automatic detection did not identify a target 8. So we want to create a new marker, because we will then end up adding it manually. We also will need to create a new marker for target 9, for 4, for 7, and for 6. So we have a bunch of targets where we don't have a pixel location, but we can add those later. So we have the eastings and the northings coordinate, we have the altitude, we also have an accuracy, that's the values from the CSV file, and as soon as we have done the alignment, we also get information about the error and the projections. Before we do the alignment, we want to make sure that our coordinate systems are set properly, because this is one of the things that happens to be wrong many times in Metashape. So if we go to our ortho model and we add our global map, we see we are somehow off the map because the coordinate system got misplaced. So we need to go back here and we need to say our coordinate system is WGS84. The camera reference is WGS84, but our markers are in the UTM zone 19F. It's really important to set those correctly because this is one of the parts that things can go wrong very often. So now we have set the different coordinate systems of the different data sets. We can also have the overall coordinate system in 19S. The projection is then being done automatically by Metashape, but it needs to know what are the input data sets, because you can tell here the GPS coordinates from the drone flights are in lat long coordinates, and the target coordinates are in WGS84 coordinates. So now as this changed to longitude, now we can zoom back to our point. We see that our markers, that our flights are at the correct location, and we can add the markers. These are the targets that we just have added. I can click off the flights. So these are the targets that we distributed throughout the area. So make sure that before you hit the alignment button that your coordinate system is properly referenced. So as the next step, we are going to perform the alignment. We are going to go to our align photos options. We don't need to manually click markers. We can do this as the next step. We are going to align the images first, and this time using a medium resolution just to make sure that we get a few more points to make it more accessible. And we also we increase our type point limit to 10,000 points. So this is something that is going to take a little while. So this is the processing that is running now for the next 20-30 minutes. And I'm going to continue the recording as soon as this processing is done. So the processing has taken some time because of the large number of images and the medium resolution, but now we do have a model that is resembling our area pretty well. So I am showing you the model, and there is still a problem with one of those areas, as you can tell. And this is something that is unfortunately pretty common when you have done flights at different elevations, and we are going to correct for this in the coming steps. So I am going to go to my target one, and now you see that there is a much larger number of images that pop up at our target one. Originally only those were identified, so you see that our target one has been identified, including an arrow bar that is pointing in this direction. This arrow bar is not very meaningful yet because we only have a limited number of targets clicked. All these other targets that you see here with a white flag are not being used yet because these targets have been identified only by their location, they have not been verified by the expert that is you. So only the ones with the green flag on it will have that. So I'm zooming in to this guy here, and I'm moving it to a more proper location, and I will need to do that for several of the points. So this is a manual steps in the manual processing that you have to put in order to ensure a higher quality product. Because of the lower resolution imagery, some of those don't end up being detected properly. So that's why we need to make sure that the location is properly be identified. You note that after you have clicked a few and moved them to the proper place, the location is pretty well identified because there is a constant update occurring based on the correctly identified targets that you have clicked. So if you want to be super precise, you do these for all of the available images that include the targets, because this will make sure that you will have the best control on your optimization process. I'm also pointing out that we have not done a camera optimization yet, but we will do so as soon as we have linked the targets, because the target location will help the optimization process. So again, as long as all of these targets are white, they are not being used, but you would like to use them because it will help you to identify more precise camera parameters. So I'm going to do this for several of those targets, and I'm going to speed up the video display here to make sure that you see the amount of work that is involved here, but you don't need to follow it in real time. And one thing I would like to point out here, that those targets that were taken, or those photos that were taken at a very high elevation, the targets don't appear to be very well recorded. And for those areas, I am not adjusting the target locations, because that would be more guessing than knowing the real target location. We are moving on to the second marker. We do the same process again. So this now here is an example where a target has not been previously identified at all. So we are now looking at a target that was not automatically identified because of the low image quality, but it's still doable to pick out the location for these, and it looks like if we can identify a sufficient number of targets here, or of images for this target, and make it a useful data collection effort. So this is the same for this next target. You see that this has not been previously identified in the automatic detection, but now that we have the images aligned, we can use the alignment information to make sure that we identify a rough target location, and then we can dive in and adjust the target. And as soon as you have clicked 4 to 5 targets, the location adjustment is working pretty well for this target. You also note that I'm not clicking every single one. It is useful to have every single one, but for the purpose of demonstrating the location clicking, I'm often using only every other one. So this is another example here where the target has not been perfectly identified, but so after having selected a few targets, I'm stressing the point, for the highest accuracy, you want to adjust every image or every target in every image that have been identified. Right now I have used a subset of these. So let's look at our model that we have developed so far. And we are going to do the refinement, the optimization in a second. I just wanted to show you a few other things. So if we are taking a photo like this, for example, we can also view the sift features that we have used to link and align these photos. So these are the sift features that have been used. All the blue points are the points that are used to link this image to another image, to the neighboring image. All the gray points are sift features that have been identified, but where no corresponding partner or pair has been found in another image. So right now we are only using those blue points, and what we are doing during the gradual selection and filtering steps, we are removing markers, or we are removing sift features that don't have a proper partner or that have a faulty match. So having said that, let's do our first optimization process and see how the output will adjust our original data set. So after the processing is done, you may have noticed that our alignment has been adjusted somewhat. There is still a problem with a few of the flights, but these can be either removed or treated with later. So right now we do have a new model that also gives us a type point variance. Obviously, we have very, very high variances and errors for those parts that we can remove in the next filtering steps. So this has not been properly aligned. This happens from time to time, and I'm going to find a position where I can remove those points by selecting them and removing them, and then I end up having a fairly reasonable setting here. So I'm going to do some more filtering steps via the gradual selection. So I'm going to select points based on their uncertainties, and in fact I'm going to make sure that my points that I have here are properly aligned. So because we have removed some points or some cameras, we are going to have a subset of these, but you can still see that the area of interest is very, very densely covered here. So because we have removed those points, it is generally advisable to rerun the optimization process, because now those points are not in the matrix that is being solved, so you end up getting a much more accurate result. And then we continue with the filtering. What you can see here is that the high elevation flights that give the overview are having a lower point density. You see the sift features are much lower than here in those areas where we have the multiple flights at different heights. There is often a problem with aligning some of those flights. You see that these borders here of this upper flight is not very well aligned. This is something that needs to be gradually adjusted by sub-selecting the points via the gradual selection. So these are points that have a higher uncertainty than the surrounding points, and we need to make sure that we end up correcting for those. So this is one of the steps that we will do next. Again, we are aiming at a overall variance value of less than 1. Ideally, we are at a value close to 0.5. So having done this recalculation, we are going to filter out some of the points. I'm pointing out we have 2.8 million points, so we don't need that high number of points. If we do a more drastic selection of a reconstruction uncertainty, we are now selecting a lot of points that have a higher quality, and we are now down even further with our accuracy. So because we have just removed 400,000 points, I'm going to rerun the camera optimization process. But I'm fairly confident that we are having a fairly good control here. That accuracy of 0.4 for this large area is pretty good. So and a variance value of 0.4 pixels as an overall maximum value for the almost 2,000 photos is pretty good. Or the more than 2,000 photos. I'm pointing out right now we only have 2016 of 2071 images aligned, because some of the images where we removed the outline of the points are not aligned anymore, but this is not crucial because those were only overview photos anyway. The more detailed low elevation flights that occurred here in this area are still in the data and will be used. So as you can tell, the optimization step is going quicker now with fewer points available, and we are going to do one step here that will be important. We want to identify the uncertainty of the targets. So if we go to reference, we see the targets, we see the easting, northing altitudes. These are the original information. This is the accuracy that we put in from the CSV file. And here we have the errors of each of the points in meters, and then also in pixels. So the target in the first row, this is target 1, is in 51 individual images, and the error, the average error of pixels is 1.3. That's pretty good, but we could go here and lower this error. For example, I would go here to the two areas of target 6 and target 7, and make sure that we have a proper target clicked, and that these are of high enough quality. So this is, for example, an image where we also have two other targets in, and we are making sure that these targets are properly adjusted. So you could do this for a few more steps. Again, it's important that these are as precisely clicked as possible. So here, target 6, they look fairly reasonable. So overall, this is a fairly good error that we have. We could improve this by clicking the points, but overall, this is a fairly good result. So if we go back to our model, we are going to do an additional filtering step using the projection accuracy. Let's go down to 20. We are removing these points. We are also selecting our reconstruction uncertainty again, and we'll filter by the reconstruction uncertainty again down to 15 to make sure that we remove the low quality points even more strongly. So now we are here at our fairly low overall error. We are running the optimization process one more time. Now we are left with 1.87 million points. So we went from almost 3 million to 1.8 million. That's still a high number. We could filter much more, but this field is pretty homogeneous, and I like what I'm seeing here so far. So this is a good good goal. You don't want to filter too much. You don't want to do too many gradual selection steps, because at some point you're removing points that are important, and also points that are important for aligning your network. So when I'm say aligning the network, I mean that the images are linked with sufficient neighbors. We can look at this network quality once we have made sure that we have a high quality output. So we have a maximum covariance value of 0.27. That's fairly reasonable. If we look at our view matches, we can pull up our matches and can, for example, identify the way how our image 0001, the first one, is linked to the image 2, for example. That's the next one in line. So these are the images, and the blue ones are the good links, the red ones are the bad links. So you can verify this for some of those images, and that allows you also then to click on an image. For example, this is an image in the center, and if we now look at our link points, we see that we have significantly more gray points, and we have a few blue points remaining because we have done some filtering. So this is generally a nice way of verifying how this network is processing. We can look also at a survey statistics. This always takes a second to generate this report. But this is a very nice way of identifying the number of images that overlap. So right now we see that those dense areas here, so the black dots are all of the photos, the UAV cameras taken with the drone, and we see that we have more than 9 images throughout this area of our interest. Looking at the camera locations, we see what the height difference is of the error estimates. What I wanted to point out is that connectivity. We have one group with 2016 images, and these are all of the images that are part of this group. This is what it's supposed to be. If you have a disconnected network, if you have multiple groups, it means that you don't have enough overlapping images, or that some other problem occurred during the alignment process. If you have multiple groups and you have areas of interest not linked, you would like to redo the alignments. So having said that, we now have a fairly good model here. We also have a camera calibration file that is based on a fairly detailed point clicking process, so I trust this camera calibration fairly well. So this will be a camera calibration, for example, that you could store and save and then use as an initial camera calibration for your next project. But again, you will need to have those targets in order to do a proper camera calibration, and the more targets you have, the better it is. So the next remaining step is to create a point cloud, and that is something that we are going to start here. I'm going to give it a medium resolution. Again, the depth filtering is medium, and this is a process that will take a while because of the resolution of the medium resolution of the images now, and because of 2000 images that are available. So I'm going to pause that recording and get back as soon as the processing is done. So this processing took a while because of the high number of images and the fairly high resolution. we see that we have generated the new product. We have the point clouds. We can look at the point cloud, and I wanted to show you one other filtering step that comes in handy from time to time. So looking at the, oops, I'm sorry, I need to move in here. So looking at the point cloud, you see it looks fairly reasonable. The resolution is higher than what we have had before. You see that the trees and also the boulders in that creek are much better depicted. So that medium resolution does certainly increase the quality of the DEM, but I wanted to point out that we can also look at the point cloud confidence, and the point cloud confidence tells you how many pairs of scenes or of photos have been used to generate this point. The blue colors indicate that multiple, sometimes several dozens or hundreds of pairs have been used to generate these points. This means that this is a high quality point because it has been identified on many photos. The reddish and greenish colors have a somewhat lower quality, and most of the times these colors are related to vegetation, because vegetation is then only seen from a few photos, or at the borders of the scene you have a lower number because you have fewer photos taken, therefore you have less overlap, and therefore you have fewer scenes. What we can do here is, first of all, we are going to duplicate that point cloud to make sure that we have the original, and then we are going to select this point cloud. We are going to filter by confidence. So we are going to select the points, let's say 0 to 5. So we are selecting the points that only occur in a maximum of 5 image pairs. So these are the points that tend to have a lower accuracy. So let me just make sure that this works. We are going to reset the current selection. We have selected the points less than 5, and you see these are the points that would be removed from such a point cloud if we are only focusing on the higher number of pairs. And you see that this is mostly the vegetation. So we did this step to verify which are the points that we would be removing if we do a filtering by confidence. And now we can do it the other way around. We can go back to our point cloud and say reset the filter. Now we are seeing all the points again, and now going to the point cloud, filter by confidence, select the confidence range, let's say minimum is 5. And then the maximum is 255. Now this would be the point cloud that would contain only the larger number of points. So if we want to create this as a separate data set, let's do this again. We reset the filter. We are going to filter our point cloud again by confidence, 0 to 5. This is the selection. We are going to select all of those points. So we are going to select all of those points, and then we are going to delete the selection. Let me just make sure that we are not selecting the markers. That was not my intention. Yeah. So we have the point cloud selected, and we are going to delete these points. And now I'm going to reset my filter. And we are left with 47 million points. So we had originally 126 million, that's our original point cloud, and now we have removed the points with a lower resolution or with a lower number of pairs, and we have a remaining point number of 74 million. So this now is a point cloud that does not contain that much vegetation anymore. We could, if you could also use a value of 10, then you would be removing even more vegetation. But right now we have a point cloud that is first of all smaller. We have not removed any of the ground points. The ground is still very well depicted, but we have removed points that are related to vegetation or points that are not that well constrained. So if you are just interested in creating a digital terrain model, so depicting the solid Earth surface, then this is a reasonable filtering step. If you're interested in vegetation height and other ecological parameters, then you definitely don't want to do that filtering step because you're removing the precious vegetation from your data set. So with these points, we can now also export the point cloud. We are going to call it La Page 2024. I'm usually giving it the name of the quality. It's a medium quality and a medium filter. MQ for medium quality, MF for medium filter, and then confidence above 5. So this is the point cloud, and I'm also making sure that I'm having this in the UTMS 19S. This is my file name. I have the coordinate system. I'm saving colors and the normals of the data set and the confidence interval. For an LAZ file, we actually don't need the normals. This is something that is more useful if you are going to work with a PLY file, or if you're doing other 3D calculations on it. But for this example, we are just removing this, and now we am storing the 74 million points in an LAZ file that then can be further processed in a different computative environment. You can use Displace, Cloud Compare, or command line tools to further classify this point cloud. As I have pointed out before, we can do preliminary classification with this point cloud using the point cloud classify ground points option. So we are going to use this filtered point clouds where we have removed the part of the vegetation through the confidence filtering, and we are going to run this because we are now talking about 74 million points. This will take a little longer. I'm pointing out in the previous point cloud at the low resolution and the low quality options, we had 9 million points. Here you see it up here, 9.7 million points. The higher resolution data set with more images, we end up having 74 million points. Therefore, the point cloud classification will take a little longer. I will let this run, and we continue the recording as soon as this is completed. So after this classification, we can also use the color coding based on classes. And we see that the brown color here is depicting the ground. And it is doing a reasonable job in identifying the ground as a ground. So we are seeing that things are, generally speaking, we can switch back and forth between, for example, oops, I'm sorry, that wasn't what I wanted to do. The colors, we see that the green color here is depicting the vegetation, and switching back to the classes, we see that the brown points are mostly depicting our bare earth. I mean, we see that at some places here, when we zoom in, that there is a little discrepancy between the vegetation and the ground, but overall, this is doing a reasonable job. So we could say that if you want to save an even more reduced data set, you can save this as a point cloud and only storing the point 2 for ground. So if we go to export point cloud and we use the same file name as before and we say ground only, then we can select here, instead of saying point class as all, we select that we just want to select the ground. And then we are going to store the confidence, the color, and we can store the classification, but we know that we are only storing the ground class. So making sure that the coordinate system is correct here, we can save this, and we are now writing a smaller number, even so it is saying that it's saving 74 million points. So I don't suggest using the classification for vegetation, buildings, roads, and man-made objects that is included here in Metashape. So this is the classified points option, because this has been optimized for urban environments or semi-urban environments, where this natural environment would need to see some more fine-tuning to produce reasonable results. So before we wrap it up here, I just wanted to go back to our reference frame and look at the uncertainties, the errors. So currently we are back to about 0.5 meter average error for the targets, which is for this large survey site okay, but you see that there is particularly one site with a larger error. So this would be something where we could go back and make sure that those markers that identify this target, this is target 4, are accurately clicked, and then maybe we can improve upon this, because we have a couple of targets that usually look very, very nice. So overall, the quality is reasonable, and we have also a point cloud that then can be further processed. For example, you can do much more detailed 3D modeling on it. You could also now generate a digital elevation model on it, and we are going to use the point cloud. We are going to select only the ground points, so we are not taking the other points into account. And because of the higher resolution, we are now talking about a roughly 11 centimeter DEM. This is something that certainly will take a second to calculate. With this DEM from the originally 11 centimeters, we then can create a 0.5 meter or 1 meter gridded version. So Metashape is internally storing this at the 0.11 meter, 11 centimeter resolution, and you can then interpolate that to the resolution of your liking. I'm pointing out that the DEM that we generated from the higher resolution flights at a lower resolution image with lower resolution images, with a subsample or downsampled images, results in a 40.4 centimeter per pixel resolution. What we are currently generating is something on the order of 11 centimeters. So let's wait till this is finished here. Okay, so now we see that our DEM has 11.5 centimeters resolution. If we bring it up, it looks fairly okay. You can zoom in more and you can see the details in it. You see those patches that are a little smoother. These are areas where we have had fewer points that belong to vegetation, for example, and that then have been filled in through interpolation. So this data set, we could export this DEM to a TIFF file. So we could say this is our LaPaya 2024 medium quality, medium filtering 1 meter DEM. And then we also should add that we are looking at confidence above 5. This is our TIFF file. And we want to create a 1 meter DEM out of it, which then creates a much smaller size. And we are saving it in the UTM 19 South coordinate system. So now you have a DTM, a gridded version that can be included in QGIS or other visualization environments. Okay, with this I hope that I could show you some relevant steps for georeferencing your data and also performing a careful camera calibration by using these targets. Showed you some quick filtering steps that allow you to reduce the data density of the point cloud, remove some of the vegetation, perform a very simple ground classification, and generate a first order digital elevation model. However, I'm stressing the fact that if you want to produce a higher quality product, you should use that point cloud in their original resolution and use external tools not included in Metashape to do the point cloud processing. You will be able to produce a better product in the end. But nevertheless, this is a useful product that can be used for several applications. One final point I would like to make regarding the resolution of the data. So we have an 11.5 centimeter DEM using the medium resolution images and a medium quality depth map generation. So if we are zooming in to one of the relevant areas here, let's look into this area here, and we are switching back to the lower resolution DEM that we have generated with a very high, very fast, with a very low quality images. We see that the level of detail that is being displayed, this is a low resolution data, this is a high resolution data. Again, this is a low resolution data, this is a high resolution data. You see that you end up having much more details in that medium quality point cloud. And if you would now do the processing on the high level, so using the full resolution images, you would have an even more detailed DEM. However, it would take significantly more time.